In this short video, I'd like to take a look at complex conjugates and give us a little reminder of algebraically how to find them, and as well as how to do so using trig form. So imagine we start out with just some complex number, z equals 3 plus 2i. Remember, we refer to 3 as the real part and the 2 as the imaginary part. Okay, so let's say we were asked to find the conjugate of this number, and often that's denoted with a bar on top. So they may write z bar, or they may say find 3 plus 2i with a bar over it. That means the conjugate of 3 plus 2i. Well, to do this algebraically is pretty easy. It doesn't change the real part. The imaginary part just changes signs. So if we had 3 plus 2i here, the conjugate is going to be 3 minus 2i. That is the conjugate of that complex number z. Okay, so if we have 4 minus 7i, then 4 minus 7i, the conjugate of that thing is going to be 4 plus 7i. All right, so to find a conjugate of a complex number, again, the real part stays the same. The imaginary part changes signs. We like complex numbers, complex conjugates, or conjugates in general, rather. You've seen where we use conjugates a lot in trig. The reason being, in particular with complex numbers, let's say I multiply two numbers that are complex conjugates, right? They have the same real parts, but opposite imaginary parts. So these are complex conjugates. If you were to distribute all this out, you would get a squared plus abi minus abi minus bi squared. Okay, notice these middle terms cancel. You get a squared minus bi squared, which we know is a -1. Oops, sorry, this should be a b squared here. So this ends up being a squared plus b squared. Now, the reason this is helpful to us is this was a complex number. This was a complex number. They both had imaginary parts to them, and we're left with just a real number. There's no imaginary component to that, right? There's no i's. So that's where it's useful to use conjugates in the context of a complex number. But we've seen in trig that we use conjugates for helping us out with identities and things like that. So let's talk about trig form and what does a complex conjugate look like in trig form. So let's start with a number in trig form. So let's how about z equal 4, let's do, how about cosine of pi over 6 plus I sine of pi over 6, right? Or remember, if you're, some people like to use the shorthand notation, 4 cis pi over 6. Remember that cis stands for cosine I sine. It's describing this format, but it's a little shorter to write. Okay, why don't we convert this from trig form to algebraic form, since we already know how to find the complex conjugate when we are in algebraic form. And this isn't, the fastest way to do the problem, but let's just see what happens. So remember, to convert to algebraic form, a plus bi, I simply clean this up, do the trig, and distribute the 4. Cosine at pi over 6 is root 3 over 2. Sine at pi over 6 is 1/2. And so then if I were to distribute the 4 into there, I would get 2 root 3 plus 2. So that's, 2i. That's the complex number in algebraic form. So therefore, the conjugate would have to be 2 root 3 minus 2i. We found the conjugate. But we can also find the conjugate straight from trig form. Okay, so let's take a look at this. Note, the complex conjugate in trig form can be found by replacing your angles with the negative angle. Let's think about that for a second. Why does that work? Remember, if you were to graph, say I've got some complex number up here, a plus bi. So it went a in the real direction, up b in the imaginary direction. The conjugate of this number, right? The conjugate of a plus bi would be a minus bi. And so if I had to graph that, I would go right A, but this time I would go down B, okay, to get to the conjugate A minus BI. And so if I'm thinking of trig form or polar form, to get to A plus BI, I would have to rotate some angle theta and march R. If I want to get to the conjugate, this time I would have to rotate down some angle. And it's the same size angle, so this would be negative theta, negative because I'm going down, and it would still be the same distance r that I walk. So we could see that to get to the conjugate, what we did is we replaced our angle with its opposite. And so simply replacing those pi over 6s with negative pi over 6s gives us the conjugate from trig form. So let's clean this up and just verify we get the same result. You can just flat out evaluate these. That's totally fine. I don't really like dealing with negatives in there, so I use the odd-even identities. Cosine is an even function, so it absorbs its negative sign. Oops. Whereas sine is an odd function, it throws out the negative sign. So that's just my approach, but everyone's got a different way. Cosine of pi over 6 is root 3 over 2. I times a half is sine pi over 6. And when I distribute the 4, I get 2 root 3 minus 2i. Same thing we got up here. All right, so two different approaches. This is just to highlight that you can find the conjugate of a complex number when you're in trig form. You don't have to go to algebraic form or rectangular form to switch the signs around. It's obtained by using the opposite angle. Okay, keep up the good work.